Hi Year 9 students. I'm Norman Wahlberger, and this is our first video where we're going to start working our way through the Year 9 curriculum. We're going to start with index laws, and in this video we're going to talk about powers of 2. Now, your curriculum that you might be following at your school might be a little bit different in order from the one that we're doing here. So the topics will be perhaps in a slightly different order, but basically I'm going to be covering the kinds of things that you're learning in Year 9, and I'm going to try to explain them to you in a relatively simple and natural way. A good way for you to organize your understanding of mathematics. Along the way, I'm going to give you some challenges or some problems to help you practice applying the ideas. So it's probably a good idea if you maybe make some brief notes in some little notebook while you're going through the videos. That would help. And especially important that you tackle the problems that I give you, the practice problems. Okay, that's how we learn mathematics, by doing it, not just listening. Alright, so what are index laws? Well, these are arithmetical rules that help us working with powers of a number. And they are very useful for working with very big and very small numbers. Index laws are also the basis for scientific notation, which is something that we're going to be learning in Year 9. So, for example, if we're interested in the distance from the Earth to the Sun, well, that's quite a long ways. And if we measure in kilometers, it's a number which is roughly this size. Let's have a look at this number. 149,600,000. So I remind you that this is the ones place, the tens place, the hundreds place. And these three numbers represent the thousands, and these three numbers represent the millions. So this is 149,600,000. And we're going to learn that another way of expressing a big number like that is in scientific notation. This is scientific notation for this number. We rewrite it as 1.496, so a decimal number there, times a power of 10, in this case 10 to the 8th. And the 8th is actually because the decimal point here has to be moved over 1, 2, 3, 4, 5, 6, 7, 8 places to get it over here. So we're going to be explaining this later on, but the point is that this use of this expression 10 to the 8th allows us to compactify big numbers, or sometimes very small numbers as well. Alright, so in this video we're going to start off by talking about grains of rice on a chessboard. Go back to ancient India. Then we'll talk about powers of 2, and then we'll introduce these positive integer index laws. So let's go back in time to ancient India around 500 AD. That's 1500 years ago. That's roughly when the game of chess was first invented. So we don't know exactly how the game arose, but there are certain legends that suggest that a king of India at that time had an advisor who was mathematically inclined, who discovered this game or invented the game, and the king was very enthusiastic because he ended up thinking it was a great game. And after playing it for a while, he wanted to reward his advisor, and so he brought him in and said, look, this is a fabulous game, it's changed my life. What do you want? Name your reward and I'll give it to you. Well, the advisor thought for a little while, and eventually he came up with a request which baffled the king because it seemed to be so modest. And here is what the advisor asked. He said, let's have a look at a chessboard. Okay, so I remind you that a chessboard is a square array. It's an 8 by 8 array. And we can draw an 8 by 8 array in the following way. If we take a square like this and roughly divide each of the sides in 2, then we get a 2 by 2 board with 4 squares. Okay, so now we divide each one of these pieces into 2, and also vertically, and then we draw more lines All right, now we have a 4 by 4 chessboard with a total of 16 squares. And now we divide each one of these ones into 2, and also these ones into 2, and draw the corresponding lines. All right, and now we have an 8 by 8 chessboard. Let's write that down here. So 8 by 8. And of course it has then 8 times 8 squares. 64 squares. Okay, so the advisor looked at this chessboard and said, okay, here's what I want, Mr. King. Please give me some rice. I would like to have 1 grain of rice for the first square. 1 little grain of rice. And then on the second grain of rice, I want to double that. So 2 grains of rice on the second one. And then on the next one, double that again, so we get 4 grains of rice. And then double that again, 8 grains of rice, and then please fill up the chessboard, and I'll take all that rice. Well, the king, who had lots of big bags of rice in his storeroom, thought, well, if I take a big bag of rice, I can probably do this very easily. This is a very modest request. And he said, oh, are you sure you don't want anything more? You're sure you don't want vast amounts of gold or big palaces? No, no, the advisor said, this will be enough. All right, so the king said, okay, let's bring in bags of rice and lay out the rice for this advisor for his prize. Okay, so what are we going to be talking about here? We're going to talk about the number 1, and then the next square has 2, and then the next square gets 4, and then we multiply each one by 2. So the next one is 8, multiplied by 2, 16, and then 32, and then 64. And we have to keep going. What we're doing here is we're looking at powers of 2. Right. So this is 2, this is 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th. Right. So we have to keep going until, well, until we get to 2 to the, well, the last square will have 2 to the 63 grains of rice on it. Okay, so that's turns out to be a very big number, and in fact it turns out that if you calculate this big total, it ends up equaling this. This is the total number of grains of rice that the advisor would have gotten if the king was able to fulfill the request. And you can see that it's a very big number. So here are sort of the ones, tens, hundreds. Here are the thousands. Here are the millions. After the millions come the billions. After the billions come the trillions. And then, well, it's not entirely clear what comes after trillions. Quadrillions or something perhaps, I don't know. So even to say what this number is a bit of a challenge. In any case, this was too much. Even if you put all the grains of rice in the entire kingdom together, you would not be able to get this total number of grains of rice. So it turns out that this was an impossible task. So I'm not actually sure what ended up happening. Maybe the king decided to change his mind and chop the guy's head off, perhaps, or something. I'm not sure. In any case, this illustrates the idea of powers of 2. It illustrates the idea that there's kind of an exponential growth. If you keep on multiplying by 2, you may start in a very modest way, but eventually you end up getting very, very big numbers. And in fact, it doesn't take too long before the numbers become very, very big. So with index laws, we want to have some tools that help us deal with these kinds of numbers. So let's have a look at these powers of 2. 2 to the 1 is the same as 2. 2 squared means 2 times 2, which is 4. 2 cubed, or 2 to the 3, means 2 times 2 times 2, which is 2 times the previous one, or 8. Then 2 to the 4th is 16. 2 to the 5th is 32. 2 to the 6th is 64. 2 to the 7th is 128. 2 to the 8th is 256. 2 to the 9th is 512. And 2010 is 1024. So 2 to the 10 is pretty close to 1,000. It's not a bad idea if you become a little bit familiar with these powers of 2. Powers of 2 come up quite a lot in mathematics in different places. Especially I want you to remember the top row. 2 cubed is 8, 2 to the 4th is 16, 2 to the 5th is 32, and I'd like you to remember 2 to the 10, that's 1024. Okay, now we come to the first index law, which tells us how to multiply two powers of 2. And the law is that 2 to the a times 2 to the b equals 2 to the a plus b. What are a and b here? Well, they're just some numbers like 3 or 4 or 5, some natural numbers. So this law actually has lots of special cases. And let's look at some examples. Say 2 cubed times 2 squared. Well, 2 cubed is 8, and 2 squared is 4. So this is the same as 8 times 4, which we know is 32. And 32 is 2 to the 5th. So we do see that, in fact, 2 cubed times 2 squared is 2 to the 3 plus 2. Right? So we could have gone from here to here directly using the index law. We just remember that when we're multiplying powers of 2, then the exponents add. 2 to the 4th times 2, or times 2 to the 1. 2 to the 4th is 16. 2 to the 1 is the same as 2. 16 times 2, I hope we can figure that out, that's 32. Again, that's 2 to the 5th. And yes, the exponent here and the exponent here have been added to get the exponent here. So this is another case of the same index law. Here's an example with a little bit bigger numbers. 2 squared times 2 to the 7. Well, the index law says that that should be equal to 2 to the 9. And we can check that by taking 2 squared, which is 4, taking 2 to the 7, which is 128, and multiplying 4 times 128. You could use your calculator, but I hope you can also do that on a piece of paper. In fact, I'd prefer that you do it on a piece of paper, maybe a little on the margin of your workbook. 4 times 100 is 400, 4 times 20 is 80, 4 times 8 is 32. If you put those all together, you get 480 and 32. It's 512, which is 2 to the 9th. And another example, 2 to the 5th times 2 to the 4th. Again, the index law says add the exponents. If you're multiplying the powers, it ends up being the same as adding the exponents. And we can check that it's true. 2 to the 5th is 32. 2 to the 4th is 16. If you multiply those two numbers, you get 512. Let me just check that for us. All right? Let's actually multiply these two numbers over here. 32 times 16. Okay. It's an important skill to be able to multiply off to the side without a calculator. We start 6 times 2 is 12. We write down the 2 and we carry the 1. 6 times 3 is 18, plus 1 is 19. So we put the 9 down there and carry the 1, which then comes down. Now we're multiplying by this 1, which is in the tens column. 1 times 2 is 2, but it has to go in the tens column because we're multiplying by something in the tens column. And 1 times 3 is 3, so that goes there. And then we add things up. 2, 9 plus 2 is 11, so we carry the 1, and 1 plus 3 is 4, plus 1 is 512. That's how we get that there. All right, so those are some examples of this first index law. When we have a law like this, it's important that you understand why it's true. So it's important, first of all, to remember the law, but it's also very valuable to understand why it's true. So that's not just a question of memorization. There's a reason why it's true, which makes it easier to remember the law. All right, so we're going to ask, why does it work? And we're going to illustrate the reason with an example. And the example will make it clear why it works. Let's have a look at this special case, 2 to the 4th times 2 to the 5th equals 2 to the 9th, and ask, why is this true? Well, remember what 2 to the 4th is. What does 2 to the 4th mean? It means that we're taking the number 2 and multiplying it by itself 4 times. 2 times 2 times 2 times 2. That's what 2 to the power 4 means. And what does 2 to the 5 mean? 2 to the 5 means 2 times 2 times 2 times 2 times 2. All right, good. So now let's look at 2 to the 4th times 2 to the 5th. What is that? Well, it's 2 to the 4th, and I'm going to put that in brackets. 2 times 2 times 2 times 2. There is 2 to the 4th. And then I'm going to multiply that by 2 to the 5th, which is here. That's 2 times 2 times 2 times 2 times 2. And that's what 2 to the 4th times 2 to the 5th is. And now if we look at this, we can see that all the operations here are multiplication. And there's an associative law for multiplication. And if you have multiplications repeated, it doesn't matter what order you multiply. If you take 2 times 3 times 4 and you multiply it in this order, giving us 6 times 4, it's the same as what you get when you take the same numbers and you combine, say, the 3 times 4 first. Right? So 6 times 4 is the same as 2 times 12. That's the associative law of multiplication. That means we don't really have to worry about the brackets. We can, in this case, just write 2 times 3 times 4. And it's completely the same whether we multiply these first and then this one, or these two together first and then this one. So using the associative law, we can write this as 2 times 2 times 2 times 2. Those are the first 4. And then times 2 times 2 times 2 times 2 times 2. There are the last 5. And now we see that altogether there are 1, 2, 3, 4, 5, 6, 7, 8, 9. Of course there are 9 2's because there are 4 here and 5 there. So altogether we're getting 2 to the 9. And I think that example makes it pretty clear that even if we replace the 4 and the 5 with some other numbers, like 11 and 28, then there'd be 11 2's and 28 2's. The total number would be then 2 to the 11 plus 28. That's why the exponents add when you multiply 2 powers. All right, now here's number 2 index law. It's 2 to the a to the b equals 2 to the a times b. We're going to illustrate things by just using our powers of 2, so I've just rewritten them up there so they're right in front of us. Okay, so let's have a look at what this index law says in some examples. It's always the best way of learning something is to look at what it looks like in specific examples. So let's have a look at 2 cubed all to the power 2. So inside the bracket is 2 cubed. What is 2 cubed? It's 8. So this is the same as 8 to the power of 2. And what does it mean when we take something to the power of 2? It means we're squaring it. We're multiplying it by itself. There's 2 copies that are being multiplied together. Not added, multiplied. All right, so 8 squared is 8 times 8, which is the number of squares on the chessboard. We've already seen that. That's 64. And 64 as a power of 2, where is it? Here it is, 2 to the 6. All right, so 2 cubed all squared is 2 to the 6th, which, yes, is indeed 2 to the 3 times 2. So we're verifying the index law. We're checking that in the case of A equals 3 and B equals 2, the law does in fact work. How about if we change the order? If we have 2 squared, all cubed. Let's have a look at that. 2 squared, what's inside the brackets is, of course, 4. So this is 4 cubed. And what does 4 cubed mean? It means we're multiplying the number 4 with itself 3 times. 4 times 4 times 4. 4 times 4 times 4. There's 3 4s being multiplied together. Can we calculate that? Yes, of course we can. 4 times 4 is 16. And 16 times 4 is, well, 4 times 6 is 24, and 4 times 10 is 40. So 24 plus 40 is 64. Which in fact is 2 to the 6th, and that's also 2 to the 2 times 3. Same law, working again. How about 2 cubed to the 3, or 2 cubed cubed? Well, 2 cubed is 8, so this would be 8 cubed. What's that? That's 8 times 8 times 8. Okay, then we could get our pencil and paper out on the right-hand side of our notebook. Work that out. That's 8 times 8. That's 64 times 8. That turns out to be 512, which from our table is 2 to the 9th. So does it work? Yes, because 2 to the 9th is 3 times 3. And what about 2 to the 4th squared? Well, 2 to the 4th is 16. If we square 16, it's 16 times 16. Again, we could do the multiplication. That turns out to be 256, which is 2 to the 8th. And that agrees with the index law because 4 times 2 is 8. So when you have an exponent to an exponent, the new exponent is the product of the exponents. So here's another example of a rule, and we would like to understand why the rule is true. And when I say understand, I mean in the way that you could explain it to one of your friends. One of your friends asked, I wonder why that rule is true. Is it just magic? Why should I believe that? I hope you can explain it to them. And here's how perhaps you could go about it. You could say, let's look at a special case. Let's look at the case 2 cubed all to the 4th power. In this case, the rule says that should be 2 to the 3 times 4, which is 12. So let's see why it is that 2 cubed to the 4th power is 2 to the 12th. And now when I say we want to see it in a way that makes it clear why it's true, not just because we're calculating this side on a calculator and we're calculating this side on a calculator and seeing that they're the same. I want to make it clear why it's true independent of actually having to calculate both sides. So we come back to the question of what are these things meaning. So what does 2 cubed mean? Well, 2 cubed means 2 times 2 times 2. So what does 2 cubed to the 4th mean? Well, when we take anything to the 4th, it means we're taking that number and multiplying it by itself 4 times. So 2 cubed to the 4th means 2 cubed times 2 cubed times 2 cubed times 2 cubed. Okay, that's what 2 cubed to the 4th means. There's 1, there's 2, there's 3, there's 4. 4 copies of this thing all multiplied together. Okay, so how can we work out what that is? Well, 2 cubed, we know what that is. It's 2 times 2 times 2. So let's put a 2 times 2 times 2 there. That's the first 2 cubed. And then the next 2 cubed is 2 times 2 times 2. And then the third 2 cubed is 2 times 2 times 2. And finally, the 4th 2 cubed is also 2 times 2 times 2. And how many 2's do we have altogether? Well, there's 3 there. And there's 4 groups of 3. So altogether there are 12 2's multiplying together. We're getting 2 to the 12th because the number of 2's is 3 times 4. 3, 3, 3, 3, for a total of 12 2's. And so the product is 2 to the 12th. That's the rule that we were trying to establish. So we've shown the rule in a way I think that makes it clear that it works even if you change the numbers 3 and 4. It doesn't actually involve us evaluating the left and right hand side, just expressing things in terms of powers of 2 so that we can see that this equals this. Okay, so here's our third and final index law, which tells us how to divide 2 powers of 2. It says that 2 to the a divided by 2 to the b equals 2 to the a minus b. Sort of complements the first index law where we had 2 to the a times 2 to the b is 2 to the a plus b. So let's look at some examples first. How about 2 to the 5th divided by 2 cubed? Well, 2 to the 5th is 32. Perhaps you remember that now. 2 cubed, I hope we all know that that's 8. 32 divided by 8 is 4. Is 4 equal to 2 to the 5 minus 3? Yes, it is, because 5 minus 3 is 2 squared, which is 4. So it works in this case. 2 to the 5th divided by 2 cubed is 2 to the 5 minus 3. How about 2 to the 10 divided by 2 to the 4th? Well, remember that 2 to the 10 was 1,024? And 2 to the 4th is 16. Okay, so then you could divide 1,024 by 16. Many of you will need your calculator to do that, but I hope there are some of you that could do that with long division. That would be great. Either way, you will get 64 if you do it correctly. And 64 is 2 to the 6th, which in fact is 2 to the 10 minus 4. So yes, the law works in this example as well. How about 2 to the 7th divided by 2? Well, remember that 2 is the same as 2 to the 1. But we don't need to put the 1 up there because 2 to the 1 is just 2. But nevertheless, you should remember that there's possibly a thinking of an exponent being 1 up there. 2 to the 7th is 128. Divided by 2, actually easy to see what that is. 8 divided by 2 is 4, and 12 divided by 2 is 6. So divided by 2 is 64, which is again 2 to the 6th. And yes, that's the same as 2 to the 7th minus 1. The exponent here is 7, the exponent here is 1. We're taking the difference. We're getting 2 to the 6th. Okay, so why does it work? Let's have a look at the first one. Why is it that 2 to the 5th divided by 2 cubed should be 2 to the 5 minus 3? Well, one way of thinking about it is to think of the division as being a quotient like a fraction. 2 to the 5th is 2 times 2 times 2 times 2 times 2. And we're dividing it by 2 cubed, which is 2 times 2 times 2. And here's another way of writing that division, which is often algebraically more useful than using this division sign. Okay? So as we proceed in mathematics, we generally use this division sign a little bit less and less and prefer to write something over something else, like a fraction, to represent the division. Okay, so if you have 2 times 2 times 2 times 2 times 2 divided by 2 times 2 times 2, how could you work to simplify that? Well, you have to remember that when you have a quotient like this, and there's a common factor in the numerator and the denominator, you can cancel that common factor and it won't change things. So we could cancel that 2 with that 2. In other words, the whole thing would be the same as 2 times 2 times 2 times 2 divided by 2 times 2. And once we've canceled one pair of 2's, well, we could cancel a second pair of 2's. So we cancel those 2's. So the answers are the same as 2 times 2 times 2 divided by 2. In fact, we could cancel 3 2's. We could cancel this 2, this 2, and this 2 with this 2, and this 2, and this 2. And that would give us 2 times 2 over 1. Okay, after you've divided the 2 here by 2, you're going to get 1. So the answer by cancellation is the same as 2 times 2, or 2 squared. And I hope that you can see that this 2 that we're getting here is really the difference between 5 and 3. We have 5 2's on the top, 3 2's on the bottom, and we're canceling 3 of the 2's, leaving 2 2's up on the top. 5 minus 3 is the 2 there. Alright, so we've established these 3 rules, which in fact you probably will have studied in year 8. So this is actually something of a review. Okay? So these are index laws where the exponents are all positive integers or natural numbers. Our first one was 2 to the a times 2 to the b is 2 to the a plus b. Our second one is 2 to the a all to the b is 2 to the a times b. And our third one is 2 to the a divided by 2 to the b is 2 to the a minus b. So these are very useful and important index laws that allow us to sort of extend arithmetic to include powers. In this case of 2, but it turns out that we could change the base from 2 to 3 to 10 to something else, and the laws would still work. Okay, now we've established these laws, it's time for a little bit of practice for you to do to solidify your understanding of these laws. Okay, so our first practice problem is to use the index laws to express each of these as a power of 2. Okay, I don't want you to evaluate them as a number, I just want you to rearrange them so that we have them in the form 2 to the something. Well, the first question is 2 cubed times 2 to the 51. Now, 2 to the 51 is a lot bigger than the numbers that we've been talking about, but still we can write down this product. Here is 2 to the 4th all squared, 2 to the 8th divided by 2 to the 7th, 2 to the 6th times 2 to the 7, 2 cubed all cubed times 2 squared, a little bit more complicated, involving 2 index laws at the same time. And again, here is also a similar kind of thing. 2 to the 4th to the 7 divided by 2 to the 13. And here are some solutions in some order. And problem 2, arrange the following numbers in increasing order. So smallest one first, up to biggest one at the end. All right, the numbers are, first one is 2 to the 4th times 2 cubed times 2 to the 5th. The second number is 2 to the 14 divided by 2 cubed. The third number is 2 cubed all to the 5th power divided by 4. And the final one is 2 cubed squared times 2 squared to the 4th power. So we want to arrange them in increasing order, and I want you to do it without a calculator. In fact, I want you to generally do all these practice problems without a calculator, if you can. All right? So I'm not asking you to evaluate these numbers numerically. It makes much more sense if you try to write each of those numbers as a power of 2, and then compare the various exponents of the powers of 2 that you get. You know, in other words, you want to rewrite them in this kind of form where it's pretty clear which ones are the bigger numbers. Right? For example, if the numbers happen to be this, it's pretty obvious this is the smallest one, and then this is the next one, and then this is the next one, this is the next one, that's the next one, and the biggest one would be that one. Great, so we've had an introduction to index laws, where we've basically reviewed stuff that you probably should have learned in year 8 mostly, but this is good preparation for our next video, where we're going to move into negative exponents. So index laws with negative exponents. We'll also move from powers of 2 to powers of 10 and other powers. All right. So I hope you'll join me for that. I'm Norman Wildberger, and we'll see you all next time.